And we're looking at our two-source interference homework here. So we have the two-source interference pattern and a bunch of different points we're looking at. So we want to know which of the points above are on nodal lines. We can draw our lines in here first, if you like. And the nodal lines are the ones with 0.5 numbers here. So it looks like we have A, B, D, G, I, J, which means that all the other letters, C, E, H, or rather F, and then H, those are all on antinodal lines. And being on a nodal line means that it's a point of destructive interference. Those waves are half a wavelength out of phase, so they're going to interfere destructively. So these are the same as those, and the antinodal lines, they're in phase, so they interfere constructively, and we get big waves there. So big waves on 1, 0, and 1, and no waves at all, flat, if everything's perfect, on 1 1/2, a half, a half, and 1 1/2. Okay, down here we have a similar setup, and we need to draw our lines in again. So we want to find first which points are on the central antinodal line. That's the m equals 0, that's only H. The first antinodal line, that's these of order number 1. So we have E, K, and J. The second antinodal line, we have B and D, and also, that's it. There's nothing. J's on, E and D. Sorry, B and D. On the first nodal line, that's 0.5. We have F and G and I. Second nodal line, nobody over there, L here, and J is on 1. Okay. And the third nodal line, A, C, M, and N. And how many wavelengths from the left and right sources are A and G? So A, we'll zoom in for this one. Alright, so starting at the bobber, 1 wavelength, 2, 3, 4, 5 and a half wavelengths from the left. From the right, 1, 2, 3, 4, 5, 6, 7, 8, and that is 9 wavelengths from the right. Nope, that doesn't work, does it? We're on the 2.5 line. They should be off by 2.5. Let's count again. So I'm using multiple representations here to check. Alright, so from the left, 1, 2, 3, 4, 5, 6. From the right, 1, 2, 3, 4, 5, 6, 7, 8 and a half. You have to look at the curvature here. Alright, so this is why we check multiple representations. Make sure that we have it right. So the difference is 2.5 wavelengths, as we'd expect, because it's on the 2.5 line. So let's look at G. 1, 2, 3, 4 from the left. 1, 2, 3, 4 and a half from the right. And it is on the 0.5 line, so we definitely expect that that would be the case. Alright, so we want to look at the difference in travel distance for points E, L, N, and M. We don't have to count all of these. It was kind of tedious and easy to make a mistake with the small lines, right, like we did on A. So if all we're interested in this is the difference, which is all that determines whether the interference is constructive or destructive, we just need to look at the order number. So E's on the one line, so it's one wavelength closer to the left than the right. L is 1.5 wavelengths closer to the right than the left because it's on the 1.5 line. N and M are both on the 2.5 wavelength line. I mean, N is way further out than M, but it's the difference that we're looking for. The difference in travel distance. And that's what the order number gives us. So we know that this will be constructive interference, and these three will be destructive because they're going to get there exactly out of phase because they've traveled a half a wavelength, or 2.5, 1.5 wavelengths difference.